Good morning, everyone. In today's lecture, we will explore one of the most remarkable achievements of ancient Indian architecture, the Buddhist stupa. Although stupas were built as sacred monuments to preserve relics of the Buddha and eminent monks, they also demonstrate advanced engineering knowledge. Their dome-shaped design, careful material selection, and durable construction techniques have enabled many stupas to survive for more than 2,000 years. Throughout this lecture, we will study the architectural components, construction materials, structural behavior, drainage systems, and famous examples of stupas, while understanding why they continue to inspire modern civil engineering. A stupa is a hemispherical or dome-shaped Buddhist monument built to enshrine the sacred relics of Lord Buddha or respected Buddhist monks. The word stupa comes from the Sanskrit word meaning heap or mound, reflecting its earliest form as an earthen burial mound. Over time, these simple mounds evolved into impressive brick and stone monuments. Every part of a stupa has symbolic meaning. The Anda represents the universe, the Harmika symbolizes heaven, the Chhatra signifies spiritual protection, and the Vedika defines the sacred boundary. Together, they combine religion, symbolism, and engineering excellence. Stupas possess several unique architectural features that make them structurally stable and visually impressive. Their circular plan distributes loads evenly in every direction, reducing stress concentration and increasing stability. The hemispherical dome efficiently transfers vertical loads to the foundation through compression, eliminating the need for internal columns. Decorative stone railings called Vedikas enclose the circumambulatory path and are beautifully carved with Buddhist stories. The large size, symmetry, and balanced proportions of stupas create a monumental appearance that reflects both spiritual importance and the engineering capabilities of ancient Indian builders. Ancient builders carefully selected construction materials based on their structural properties and durability. Burnt bricks formed the inner core because they provided high compressive strength while remaining economical. Dressed stone was used as an outer protective layer, improving durability and appearance. Lime mortar bonded the bricks and stones together, offering flexibility to accommodate small settlements without cracking. Fine-grained sandstone was chosen for decorative railings, gateways, and sculptures because it was easy to carve and resistant to weathering. This thoughtful combination of materials demonstrates a sophisticated understanding of material behavior and structural performance. One of the greatest engineering achievements of the stupa is its hemispherical dome. When loads act on the dome, they are converted into radial compressive forces that travel smoothly along the curved surface and finally reach the base. Since masonry performs exceptionally well under compression, the dome remains highly stable without experiencing significant tensile stresses. This efficient load transfer eliminates the need for beams or columns inside the structure. The geometry itself provides strength. This is why many ancient stupas have survived earthquakes, weathering, and the passage of time for over 2,000 years. The structural stability of a stupa depends on three important engineering concepts. First, the circular shape resists wind and earthquake forces because stresses are distributed uniformly without weak corners. Second, the thick masonry walls provide enormous weight, increasing resistance against overturning while improving thermal insulation and durability. Third, the broad circular foundation spreads the structural load over a larger area, reducing soil pressure and preventing uneven settlement. Many stupas were also constructed on compacted stone platforms to improve foundation performance. These principles continue to guide engineers in designing stable and durable structures today. Effective drainage is essential for preserving masonry structures, and ancient builders understood this remarkably well. Stupas were constructed on raised platforms that protected them from groundwater and flooding. Their curved dome surfaces allowed rainwater to flow quickly without accumulating. Perimeter drainage channels carried runoff safely away from the foundation, reducing erosion and moisture damage. Lime plaster coatings further protected the masonry by resisting water penetration. These drainage techniques minimized deterioration and significantly increased the lifespan of the monument. Modern civil engineering still applies similar principles in foundation protection and water management systems. Two of India's most famous stupas are the Great Stupa at Sanchi and the Dhamak Stupa at Sarnath. The Great Stupa at Sanchi, originally built by Emperor Asoka in the 3rd century BCE, is the oldest surviving stupa and a UNESCO World Heritage Site. Its beautifully carved gateways depict important Buddhist stories. The Dhamak Stupa marks the location where Lord Buddha delivered his first sermon after attaining enlightenment. Its massive size, stone carvings, and historical importance make it one of the finest examples of Buddhist architectural heritage. The Barhut Stupa and Amaravati Stupa are equally significant in the history of Buddhist architecture. Although the Barhut Stupa is largely ruined today, Its sculptured railings preserve valuable information about early Buddhist art and inscriptions written in Brahmi script. The Amaravati Stupa, constructed under the Satavahana dynasty, was one of the largest and most richly decorated stupas in ancient India. Its marble relief panels display outstanding craftsmanship and artistic excellence. Together, these monuments demonstrate the architectural diversity, engineering skill, and artistic achievements of ancient Indian civilization. To conclude, the Buddhist stupa represents a perfect combination of architecture, engineering, and spirituality. Its circular plan and hemispherical dome demonstrate efficient load distribution, while the intelligent use of bricks, stone, lime mortar, and sandstone reflects advanced knowledge of construction materials. Raised platforms and drainage systems ensured long-term durability by protecting the structure from water damage. Even after more than 2,000 years, many stupas remain standing, proving the effectiveness of these engineering principles. As civil engineers, studying these ancient structures helps us appreciate sustainable design, structural efficiency, and the timeless value of good engineering practices.